Imagine stepping into an elevator. You press the button for space. The doors close. You start to rise. 8 days later, you step out 36,000 kilometers above the Earth. No rocket, no fuel, just a cable and a very long ride. This is not science fiction. This is an engineering problem, and we are closer to solving it than you think. The concept is simple, deceptively simple. You anchor a cable to the Earth's surface near the equator. You run it straight up, through the atmosphere, through low Earth orbit, through the Van Allen belts, all the way to geostationary orbit, 35,786 kilometers up. That's where a satellite orbits at exactly the same speed the Earth rotates. It hangs in one spot in the sky forever. But the cable doesn't stop there. It keeps going. Past geostationary, out to a counterweight at 100,000 kilometers. That counterweight pulls outward like a ball on a string. Centrifugal force holds the whole structure taut. No towers, no supports, just tension all the way up. Now attach a climber, a mechanical car that grips the cable and ascends. Power it with a laser beam from the ground, load it with 10 tons of cargo, and send it up. That's it. That's the space elevator. The idea is not new. In 1895, Konstantin Tsiolkovsky, the father of astronautics, looked at the Eiffel Tower and imagined extending it all the way to orbit. In 1979, Arthur C. Clarke wrote an entire novel about it, The Fountains of Paradise. Clarke said something that stuck. He said the space elevator will be built about 50 years after everyone stops laughing. People have mostly stopped laughing. In 2003, NASA funded a serious study. Bradley Edwards, a physicist at Los Alamos, published a detailed design. A ribbon 1 meter wide and thinner than paper, tapering from geostationary down to the surface. Total mass about 800 tons. Estimated construction cost, $10 billion. Edwards even picked the location. A floating platform in the eastern Pacific, west of the Galapagos. Far from hurricanes, far from air traffic, far from geopolitical complications. Everything in his design worked. Except one thing, the ribbon. This is where the blueprint meets reality, and reality has a problem. A space elevator cable must support its own weight across 100,000 kilometers. The stress is enormous. You need a material with a specific strength, that's tensile strength divided by density, of at least 63 gigapascals. Steel, 2 gigapascals. It would snap under its own weight after about 30 kilometers. Kevlar, 3.6 gigapascals. Better, but not close. Carbon fiber, 7 gigapascals. Still not enough. Carbon nanotubes, single tubes of carbon atoms rolled into cylinders just 1 nanometer wide, have a theoretical tensile strength of 130 gigapascals, more than double what we need. On paper, the problem is solved. But here's the thing about carbon nanotubes. A single tube is extraordinary. A fiber made of billions of tubes is not. Defects, misalignment, weak junctions between tubes. In practice, the best carbon nanotube fibers we've made reach about 8 gigapascals. A breakthrough in 2024 pushed dynamic strength to 14 gigapascals. Still less than a quarter of what we need. The gap between a single perfect nanotube and a usable cable is the gap between a diamond and a handful of graphite dust. Same atoms, completely different material. And the cable isn't the only problem. The space elevator passes through low Earth orbit, the most crowded junkyard in space. 26,000 tracked objects. Millions of fragments too small to track but fast enough to cut a cable. At orbital speeds, a fleck of paint hits like a bullet. At the surface, the anchor station faces lightning, hurricanes, and salt spray. The cable itself would vibrate, oscillations driven by the moon's gravity, solar wind, and the climbers themselves. And the climbers need power, megawatts of it, beamed from ground-based lasers through an atmosphere that absorbs and scatters light. Every layer of the blueprint adds another warning. Now imagine the worst case. The cable breaks. If it snaps below geostationary orbit, say at 25,000 kilometers, two things happen simultaneously. The lower section loses its upward pull and begins to fall. It doesn't plummet straight down. It drapes eastward along the equator, thousands of kilometers of ribbon fluttering down like the world's longest streamer. Lightweight enough that it won't cause catastrophic damage, but dramatic enough to make the evening news. The upper section, still spinning with the Earth, has too much centrifugal force and not enough weight to hold it down. It flies outward, into a higher orbit or out of Earth's gravity entirely. Gone. The detentioning wave travels through the cable at over 1,000 meters per second. Faster than a rifle bullet, the whole structure unravels in minutes. But here's what I find most interesting about the space elevator. We can't build it on Earth, not yet. But we could build one on the Moon, today. The Moon's gravity is 1/6 of Earth's. It has no atmosphere, no wind, no lightning, no weather. The specific strength requirement drops dramatically, and materials we already manufacture, Kevlar, Xylon, Dyneema, are strong enough. A 2019 study from Columbia University proposed a lunar space elevator using existing commercial fibers. Estimated cost, about $1 billion, not $50 billion, not a century away. Buildable now with materials you can order from a catalog. The lunar elevator got almost no attention. The Earth version got a novel, a NASA study, and 100 YouTube videos. The one we can actually build, barely a footnote. So where does that leave us? Every component of the space elevator has been designed. The climbers work, the anchor works, the counterweight works, the economics are transformative. $200 per kilogram to geostationary orbit instead of thousands. Solar power satellites, orbital factories, routine access to space like a freight train on a schedule. Everything works, except the string. Arthur C. Clarke said 50 years after everyone stops laughing. People stopped laughing about 20 years ago. The question is no longer whether this is a good idea. The question is whether we can make a cable strong enough to hold it. And somewhere in a lab, someone is trying to make a carbon nanotube fiber just a little bit longer, just a little bit stronger, just a little bit closer to the blueprint. This is Stardrift FM. Keep drifting.